In this particular section, we are going to understand how to determine the modulus of a complex number. So we have a complex number z given by a plus ib. Then its modulus, also known as the absolute value, is denoted by mod of z. So we have mod of z, and this value is given by, we have assumed that mod of z is a plus ib. Then this value is going to be equals to the real part of the complex number a plus ib, which is a. So we square it and add it to the imaginary part, which is b. So while writing here, we have to be careful that when we are taking the imaginary part, we are actually considering only the real number associated with the imaginary part, that is b. So let's be careful that whenever we're finding the modulus, don't get confused by writing it as square root of a squared plus I times b whole squared. Now, these things will evidently become clear when we do the geometrical interpretation of complex numbers, but it will come a while later. So let us stick to how to calculate the modulus of a complex number. For example, one more thing here, it's mentioned here that a and b are real numbers. So since we have a real numbers, then where sum of the square of a real number is going to give us a real number, and the square root of that particular real number is always going to be greater than or equals to 0. Let's take an example. So let's say we have a complex number z given by 2 plus 3i. Then the absolute value of this complex number z will be simply equals to the square root of the real part, which is 2 squared. 2, we square it and then add it to the imaginary part. The real number associated with the imaginary part is 3, so that is b. So b value is 3, so we write it as 3 squared. And the value will be equals to 4 plus 9, which is equals to square root of 13. So we see that the value is a real number. So this is a real number. This is no longer complex, and this value is simply greater than 0. Now there's one more thing we can take use, where modulus becomes absolutely important. So let us say we have a complex number z1 given by, let's say, 3 plus I. Then we have another complex number z2, 3 plus 2i. And a third complex number, 3 plus 3i. Now if we ask the question which one of this complex number is the greatest or which one of the smallest, makes no sense. Meaning we can never say that z1 is greater than z2 or z2 is lesser than z3. Saying this has no meaning. However, if we are to find out the modulus value of z1, then this value will be 3 squared, which is 9, plus the value of b will be 1, which is 1. So this gives us square root of 10. Then the modulus of complex number z2 will be 3 squared plus 2 squared, which is equals to square root of 9 plus 4, that gives us 13. And if we finally find out the absolute value of z3, that will be 3 squared plus 3 squared, which will be square root of 9 plus 9, which is 18. Now it becomes evident that clearly that the absolute value of z3 is greater than the absolute value of z2 and the absolute value of z1. So this is where we can say that the magnitude of the given complex number z3 is the greatest and that of z1 is the smallest. So now that we have understood how to find the absolute value of a given complex number, let us talk about some of its properties. So the first property says that for a given complex number z, if the absolute value of the complex number is 0, that means the complex number itself must be 0, or vice versa. So let us try to understand what it means. So here it's mentioned that z is a complex number. So let us suppose that the value of z to be equals to x plus iy. Now we find out the absolute value. So absolute value of the complex number z will be simply equals to square root of x squared plus y squared. Now suppose absolute value of z is equals to 0. So that would mean that the square root of x squared plus y squared is equals to 0. Or we can say that x squared plus y squared is equals to 0. Now we have sum of the squares of two real numbers and this value is 0. This is only possible, no matter what value you choose, this equation is only possible when x is equals to 0 and y is equals to 0. There's no other such value for x and y that will make the above equation true other than x and y both being equals to 0. So that means when we substitute into our complex number, so we get 0 plus I times 0. So we get a 0 complex number. The other way around, if we have a complex number z given by 0 plus I times 0, then its absolute value is going to be equals to 0. So this is proof number 1. And the second part, let's go to that. So, and this is our proof for number 1. Then you go to the second part. So second part says that given a complex number z, then its absolute value is equals to the absolute value of the conjugate, which is also equals to the absolute value of the negative times the complex number. So let us begin by using the same assumption. So let's do proof number 2. So let us begin by assuming that the value of the complex number z is x plus iy. Then its conjugate will be z bar is equals to x. So we replace I by negative I. So that gives us x minus I times y. Then we take the original complex number z and we multiply it by negative 1. So we have negative multiplied to x plus iy, which gives us negative x minus I times y. And if we write it in the standard form, so we have negative x plus I times negative y. So we could write the conjugate in the standard form, and that would give us x plus I times negative y. Now we try to find out the absolute value of each of the complex number. So for the first one, we have absolute value of z to be equals to square root of x squared plus y squared. Then we find the absolute value of the conjugate of the given complex number, and that would be x squared plus negative y squared, and that also gives us x squared plus positive y squared. And finally we have the negative absolute value of the negative complex number z, so that would be simply negative x squared plus negative y squared, which will be also equals to x squared plus y squared. So we see that the absolute value of the three complex numbers are equal, so we can safely say that the absolute value of a given complex number z is always equals to the absolute value of its conjugate to the negative of its complex number, which in turn is equals to the absolute value of its conjugate. So these are the two properties. Let's move on to the next two properties. So in the third proof, we are given a complex number z. Then we can always find the upper and the lower bounds of the real part of z. This goes well for the imaginary part of z as well. So let us begin with proof number 3. So let us begin by assuming that the value of z is given by a plus I times b. Now we find out its absolute value. So the absolute value of z is equals to square root of a squared plus b squared. Now what is saying that when you find out the real part of z, the value is equals to a. That's saying that the value of a is always greater than the negative of the absolute value of z, which is square root of a squared plus b squared, and it's lesser than simply square root of a squared plus b squared. Or in other words, it can say that a square root of a squared plus b squared is the absolute value of z, and we have absolute value of z. So the real part of the given complex number z lies between the absolute value of negative z and positive z. We can check this out with an example. So let us assume that the value of z is equals to 2 plus 3i. So we have the absolute value of z to be equals to square root of 2 squared, which is 4, plus the square of 2, which is 4, and the square of 3, which is 9, and that gives us square root of 13. Now square root of 13 will be approximately equals to, we use a calculator, we have square root of 13 its value is 3.6. So its value is approximately 3.6. So here we'd say that the real value of z is 2, and we can see that the value of 2 is greater than negative 3.6, and it's lesser than positive 3.6. So it makes sense. So the real part of z is always going to be lying between the absolute value of negative z and positive z. The same goes true for the imaginary part as well. So if we look at the imaginary part of the complex number z equals to 2 plus 3i, so we have imaginary part equals to 3, and that holds true as well. So we have the 3 value is greater than negative 3.6 and lesser than positive 3.6. So we also have that the imaginary part of, so let me rewrite it. So for this we have the real part of z lying between negative z and positive z, and so the imaginary part of the complex number z has its value lying between the negative z and positive z. So this is proof number 3. Now we go to proof number 4. Proof number 4, let me change the color. So proof number 4 is a very important proof. It has countless application that we will be finding in some later part of this section. So it's given that for a complex number z, then the product of the complex number z to its conjugate is a real number, and it is the square of its absolute value. So we have, suppose z to be equals to x plus I times y. Then its conjugate will be simply x minus I times y. So let us find the product z times z bar. That gives us x plus iy multiplied to x minus I times y. Now we can apply the identity a plus b multiplied to a minus b is simply a squared minus b squared. So this gives us x squared minus I squared times y squared, and we know that the value of I squared is negative 1, so x squared minus of negative 1 times y squared is simply going to be positive y squared. Now x squared plus y squared can be written as the square root of x squared plus y squared whole squared. Now this was done so that we can substitute the value of square root of x squared plus y squared by the absolute value of z, which is as per definition. So this square is there, so we have the product of z times z bar is equals to the absolute value of the complex number z squared. If we use property number 2, prove property number 2, then we can say that this is also equals to the absolute value of the conjugate square, or we can say the absolute value of the negative complex number squared. This is always going to be true. Let us go to the next proofs. Proof number 5. It states that if we have two complex numbers z1 and z2, then you first take the product of the two complex number and then find the value of the absolute value is equivalent to finding the absolute value and then taking the product. It will give us the same result. So let us begin. By assuming that the value of z1 is given by a plus ib, and the second complex number z2 is equals to c plus id. Let's also find out its absolute value as we go along. So the absolute value of z1 always simply equals to the square root of a squared plus b squared, and the absolute value of complex number z2 will be equals to the square root of c squared plus d squared. Now we begin with the left hand side. So we have first find out the product z1 times z2. So that will be a plus ib multiplied to c plus id, and that should give us a times c plus id plus ib multiplied to c plus id. So this is equals to a times c plus I times AD plus I times BC plus I squared BD. So this fourth term will become a real number because I squared is equals to -1. Then we combine the two real parts, so we'll have AC minus BD plus the imaginary part. So we factor out I, that leaves us with AD plus BC. This is the value of the product of the two complex numbers z1 and z2. Now let us try to find out the absolute value of the product, and that should give us the square root of the real part, which is AC minus BD squared, added to the square of the imaginary part, which is AD plus BC. So this is the absolute value of the product of the two complex number. Now in the second part, what we do is we're going to let's expand this given complex number. So we'll have so we have the absolute value of z1 times the times z2 is equals to square root of a squared c squared minus 2 times ACBD plus B squared D squared plus A squared D squared plus 2 times ADBC plus B squared C squared. So here we have applied excuse me. So here we have applied the expansion of a minus b whole squared and a plus b whole squared. Now we see that 2ac negative 2acbd is going to cancel out 2adbc, leaving us with square root of a squared c squared plus b squared d squared plus a squared d squared plus b squared c squared. So now we are going to combine the first term and the third term by factoring out the common value, which is a squared, and that gives us a squared times c squared plus d squared. So in this part we are combining the first term and the third term. Then we'll combine the second term and the fourth term by factoring out the common value, which is b squared, and that leaves us with c squared plus d squared. Now we have two terms, and in both the terms we have c squared plus d squared common. So we're going to take c squared plus d squared, which will be multiplied to a squared plus b squared. Now we can separate the two, separate into two roots or the square root values. So that would be simply the product of the square root of a squared plus b squared times the square root of c squared plus d squared. I've already found out that square root of a squared plus b squared is the absolute value of the complex number z1 multiplied to the square root of c squared plus d squared, which is the absolute value of the second complex number z2. So this proves that when we take the product of two complex number and then find out its absolute value, then this is exactly equals to the modulus of z1 times the modulus of z2. Let us go to this next proof. So in proof number 6, we are given two complex numbers z1 and z2. Then if we divide z1 by z2 and then take the absolute value, this is the same as finding the absolute value of the individual complex number first and then dividing them. So let us try to prove this using general complex numbers, meaning we'll assume that z1 to be equals to a plus ib, and that gives us the absolute value z1 to be equals to the square root of a squared plus b squared. Then we take another complex number z2, which is equals to c plus id, and that gives us the absolute value z2 to be equals to c squared plus d squared. Now we begin with the left hand side. So we have z1 over z2. We'll first find out the division, or we'll find the value of z1 divided by z2 and then take the absolute value. So we have a plus ib in the numerator, which is divided by c plus id. Now the first objective will be to convert this into a standard form. So in order to do that, we have to multiply the numerator and denominator by the complex conjugate of the denominator, which is c minus id. Now we do the multiplication. In the numerator, it will be a multiplied to c minus id, which will give us ac minus I times ad, plus ib times c minus id will give us I times bc minus I squared bd, divided by c plus id times c minus id is simply c squared plus d squared. We have done multiple problems based on this. So that gives us ac plus bd plus I times bc minus ad, divided by c squared plus d squared. So this is the value of z1 divided by z2 in its standard form. Now what we're going to do, standard form is like I didn't separate it here. Let me do it in the next line. So this gives us z1 over z2 equals to ac plus bd. Or we can do one more thing. What we can do is we factor out 1 over c squared plus d squared and then write the numerator in the standard form. So that would be ac plus bd whole square, mistake, ac plus bd plus I times bc minus ad. Now we'll try to find out the absolute value of z1 over z2, and that will be the absolute value of 1 over c squared plus d squared is simply going to be 1 over c squared plus d squared, because that is a real number. So absolute value of a real number, it's the real number itself. Or let's simply put an absolute value here, and the absolute value of the complex number will then be ac plus bd squared plus bc minus ad squared. So we have the absolute value of z1 over z2 is equals to, so we have 1 over c squared plus d squared, which is always a positive number no matter what the value of c and d are. So we can simply write it as 1 over c squared plus d squared without the absolute sign. Now we work out with the value inside the square root. So that would give us a squared c squared plus 2 acbd plus b squared d squared plus b squared c squared minus 2 bcad plus a squared d squared. Now 2acbd is the additive inverse of 2bcad, so they will cancel out, and that leaves us with 1 over c squared plus d squared, the square root of a squared c squared plus b squared c squared plus b squared d squared plus a squared d squared. Now we're going to take c squared as the common factor from the first two terms. So we have c squared multiplied to a squared plus b squared, plus we take out d square as the common term from the third and the fourth term. The d square is the common factor, so we have d squared multiplied to a squared plus b squared. Then we do a little bit of factorization here, so that will give us 1 over c squared plus d squared times square root of a squared plus b squared. So we have factored out a squared plus b squared from the first term and the second term, and then we multiply it to c squared plus d squared. Now we are going to bring the term and from outside the square root inside the square root, so that would be simply divided by c squared plus d squared whole squared. So what this has been done so that we can factor out c squared plus d squared from the numerator and denominator, one of the term, and that finally leaves us with square root of a squared plus b squared divided by the square root of c squared plus d squared. So this is the value of z1 over z2 and its absolute value. Now we know that the square root of a squared plus b squared is simply the absolute value of z1 divided by the absolute value of z2. So this is the required proof. Now when does this proof becomes useful? So let us do one example here. So take a space. So let's say we have two complex numbers z1 given by 2 plus 3i and z2 is equals to 3 plus 2i. Now we have to divide z1 by z2 and then take its absolute value. So instead of doing this, that would take us in a longer route. So we have 2 plus 3i divided by 3 plus 2i, that's absolute value. So if we take the usual route, we have to convert 2 plus 3i over 3 plus 2i into the standard form and then take its absolute value. But instead what we can do is we can take the absolute value of the numerator divided by the absolute value of the denominator, and that will be equals to square root of 2 squared plus 3 squared divided by the square root of 3 squared plus 2 squared, and this value is simply equals to 1. So this is a faster way of finding out the absolute value of z1 over z2.